I'm really happy to announce our next guest speaker for the course, Professor Jiajun Wu. So Jiajun is an assistant professor here at Stanford in the Department of Computer Science, and he's a faculty member of the Stanford Vision Vision and Learning Lab. His research focuses on scene understanding with an emphasis on multimodal perception, robotics and embodied AI, visual generation and reasoning, and 3D understanding, which is the topic of today's lecture. And so I'll now turn it over to Jiajun to begin today's lecture.
Okay, yeah. So I'm Jiajun. I'm an assistant professor here, and I think a few years ago I used to teach this class, co-teach. So I heard this year it's the 10th year anniversary, right? So you have guest speakers from different places. Okay, so today we're going to talk about 3D vision. So it might be kind of different from a lot of things you learned before, because I think in the past few weeks we talked about like convolutional neural networks and transformers and maybe vision language models and generative models as well for adjusting, right? Okay, yeah. So here for 3D, I think I'm going to first introduce a little bit on what are the 3D representations. You know, so it's more like it's pretty distant from all the deep learning stuff. But then we're going to talk about how deep learning or AI has changed 3D vision and how they can be integrated in different ways, you know, and we'll look into a few different applications about 3D generation, reconstruction, stuff like that. Okay, so let's begin by looking into what are the possible ways to represent objects in 3D, because in 2D it's so straightforward. It looks like, okay, I just have pixels, right? I have I'm loading a file of a PNG file, a JPEG file, it's like 200 by 200 pixels. But how can we represent 3D objects? I think that's the first thing we want to look into. And 3D objects, you know, they can be diverse. They can be at different scales. It can be like huge, large buildings and trees, complex structures. And if you zoom in, you know, you can also see all the fine details. So what are the best 3D representations to represent all these different types of 3D objects at different scales with different features? And unlike images, where everyone just uses pixels, you know, so we have 200 by 200, 500 by 500. The way to represent 3D objects, objects are also like you have geometry, you have textures, you have materials. But let's just maybe start by looking at geometry. And even just for 3D object geometry, there are so many different ways to represent them. You know, we can basically categorize them into two different categories. One is called explicit representations. So where you can, in some sense, they're directly, I would say, explicitly representing part of the objects. This includes things like point clouds. If you have a cloud of 3D points, or a polygon mesh, or subdivisions, which we're going to talk about it, and others. And there's a different categories of object shape representations, which are often called implicit. So we're going to talk about them as well. So I'm going to explain them in a little bit detail later, including level sets, algebraic surfaces, distance functions. So they're basically representing 3D objects or their geometries as functions, which it is not directly, you know, it's not as, in some sense, intuitive as, oh, it's just a collection of points. But as we'll see later, they also have their own advantages and weaknesses using implicit representations. So every choice, they have their, you know, suitable task and type of geometry. In particular, in the context of deep learning, you know, they may also have their own strengths and weakness when you want to apply a deep learning method on top of it. So when do we choose representation? You know, we have to store them. So pixels are easy to store because it's just a matrix. But then 3D point clouds are kind of more irregular. And also, you know, especially if you use some implicit representations, like representing object as a function, how would you store that in a computer? And how does it support, you know, creating of new shapes? And especially now, let's say maybe the input is a picture or the input is a language descriptions. And different type of operations. You have a 3D objects, and then how can you edit it, simplify it, smooth it, filter it, and repair it? Right, so you can have to do a lot more. You know, for images, sometimes you want to do that too. You want to edit it. You want to edit it using language. You want to edit it using stroke. And how can you edit or perform any type of operations on 3D objects? And rendering, how can you turn that 3D objects render into into 2D pixels? In some sense, 3D vision is to invert the process, right? How can you go from 2D images to reconstruct the 3D objects? So how does it support all these different things, including end-to-end animations, especially if you are modeling, let's say, 3D humans or animals, and you want to animate them. So all these factors need to be considered. And something else, of course, it sort of connect through all these is also their integration with different deep learning methods for, let's say, shape editing, rendering, inverse rendering, animation as well. So very quickly, we can go through some of these representations like point clouds. So point cloud is probably the simplest representations. It only has 3D points. It doesn't have connectivity, so it doesn't capture how these points are connected. So you basically just have instead of having an n by n matrix, which is about the pixel values of all the pixels in a picture, now you have a 3 by n matrix where 3 is XYZ coordinates of these individual points, and you have a number of points. So sometimes you can represent the surface normals of the point as well, so that you have not only where the point is in the 3D space, but also to which direction it's facing. So you have the surface normals, which give you a bit more information. And sometimes people call them surfals, which is points with orientations. And yeah, so why do you need surface normals? Because if you want to render them, you want to say how the object look like. Then that means you have to often specify a lighting source, right? Where's the lighting coming from? But to make the rendering look realistic, you have to consider how the lighting, coming from a certain direction is going to interact with the point. And this is where the surface normals is used to help you to make the rendering look realistic, like you can see here. So how can you get points? A benefit of the point cloud, it is often a raw format that you will get from a lot of the 3D sensors, including these kind of depth sensors, including some 3D scanners. And, nowadays, I think if you can even use an iPhone, I think they have an AR kit or these kind of software allow you to scan 3D objects, but the raw output of those sensors, they're still kind of 3D point clouds. Now, of course, after that, you have to process them and fuse them to make it like maybe objects with textures. They often results from scanners. They can potentially be very noisy, and there are things like this, and then you want to fuse them, merge them, repair them. In this part, you have to consider how these different pictures can be registered to give you the shared point cloud. And they're very flexible. So because you can move points here and there, so you can use them to represent basically any type of object geometry. You're not constrained by the topology or stuff like that. It's kind of useful for large data sets because sometimes you have to consider a very diverse set of objects. But because the points are already in some sense you consider to have being pre-sampled, right? So, if you have a lot of points, if you're representing objects but your points are sampled in an uneven way, in the sense that you have a lot of points, let's say on the head of the rabbit, but you have very, very few points on the tail of the rabbit, then it will be actually hard to draw samples from these inner sample regions. So sometimes when people consider, sampling points, you have to design algorithm to make sure you sample them roughly evenly, across different parts of the objects. And other limitations are, it's not obvious how we can directly perform sometimes the very useful operations like simplification or subdivisions on these objects. It doesn't directly allow you to do smooth rendering. There's no topological information, right? So for example, here, if I give you a collection of points, then you can't even tell, if this is like a torus or this is like these kind of ring-like shapes, right? Because it doesn't tell you how these points are connected. So it's kind of a partial information about what the object is if you just have the point clouds. So naturally, people will say, okay, how can I actually capture more information so that I can distinguish between these two different objects? Then naturally, that goes to the polygonal meshes. Right, so it represents the objects as still as a collection of points, but then also how these points are connected. So now you have not only the points, but also the faces, the surfaces. And this is arguably I would say the most widely used representations for 3D objects in all these graphics engines, in computer games and stuff like that. Basically it is all represented as polygon meshes. But you can see that, to represent faces, it is more complex because often you have to consider, especially if you're looking at raw meshes, then every face may have a different number of points. It may have 3 points, it may have 4 points, it may have 5 points, and how you can represent them, especially given their irregularity, how you can integrate them with neural networks, especially in the early stage when people start with convolutional neural networks. Okay, they always assume a fixed resolution. But here you have, not obviously a variable dimension of these raw information. How does that integrate with deep learning? That has been some big challenge. That's why, deep learning with 3D vision kind of started kind of late because people are thinking about how we can adapt all these deep learning methods to deal with all these complex representations for objects, which are not as unified as images. But meshes are really widely used, and they can be, very complex meshes that capture all the details. For example, you have scanners, you get points, and then you fuse them, and you apply some algorithm. You can get, very large mesh. This one has 56 million triangles and 28 million vertices. to represent a sculpture. And you can have even larger ones. Let's say from Google Earth, they have trillions of triangles try to represent basically all the buildings on Earth. The nice thing about meshes, it supports a lot of operations like subdivisions. Oh, I want to have more details, and how can I use more meshes to capture more details of the shape? And you can do simplification as well. Sometimes you want to process things very fast. So I don't need that many meshes. I just want to simplify it. And so there are existing algorithms that allows you to do that as well. And regularization. If you get an irregular mesh, and sometimes you want to regularize them so that every face is a triangle. They always connect 3 vertices. They have roughly the same size, and so that it's easier for processing, and they have more, obviously, good properties that supports future processing of different graphics algorithms. And meshes, there have been people who develop these algorithms as well, so that you can ensure that, basically points at different regions, they're roughly evenly sampled, so that it won't be the case that, okay, let's say the head of the tail, or the head of the rabbit is much more densely sampled than the tail, and these kind of things. Okay, so this is a kind of one type of shape representations, and there are other type of shape representations, for example, parametric representations, because objects are not just totally irregular. It's not just often a collection of points and meshes. They're very general, but sometimes you lose a lot of information. If you look at, let's say, your chairs or the tables, you have all these kind of straight lines, right? So how can you represent these kind of straight lines? And when people design them, they often use some of these parametric representations. So you can represent shapes as a function, right? So think about it, so when I design them, I can, it's really, if I want to represent a surface or represent a curve, right, the underlying degree of freedom is actually lower. Often, if I have a curve, there's only one underlying degree of freedom. That's why I can represent a curve using a function f of x, right? I just vary the x and get a value of y. So you can use basically all these different types of functions in 2D, but also more often in 3D, right, to map a certain number of variables, the underlying intrinsic dimensionality of the objects, which are often, let's say, in 2 or even 1, and then map it into the 3D space. And then this allows you to represent the 3D objects in the parametric representations using basically a set of functions, right? You can do that for curves. Let's say in circles, right? Basically, if you want to represent a circle, you don't really need one way is you sample a number of points, right? Or you can even connect them like a meshes, using the lines. Another way is you just represent the curve, the circle as this function, right? Basically, there's a sine function and a cosine function, and you just vary one variable, which is t. You can think about it as the degrees or the angles, and it will map it to all the points on the circles, right? So here now you can use a function to represent a parametric representations for curves in 2D, and of course you can do that in 3D as well. If you want to represent a sphere, all you need is just like 2 degrees of freedoms, U and V, and then you can go through these functions so that you can map them to every point in the 3D space for this sphere, right? So people have designed, I'm not going to detail here, but more complex parametric representations like Bezier curves and Bezier surfaces, which allows you to represent these kind of pretty flexible and smooth surfaces in 3D using basically a few control points. So you basically use these Bezier functions to capture the underlying lower dimensionalities of these surfaces, and then you can map the underlying low dimensionality into these kind of flexible shapes. And they also allow you to do things like subdivision, so you can, trying to get more details into the surfaces and to make it more fine-grained and stuff like that. Okay, so that would be the second category of shape representations. You can represent 3D objects in a non-parametric way, like a collection of unordered points, or their connections as in meshes, or you can represent them in a parametric way where you have a function basically, and by varying a few parameters that are underlying the true degree of freedoms of the object geometry, you can map them into more complex shapes. So basically everything here, as I said, it has been, if you remember at the very beginning, we said there are 2 types of ways to represent object geometry. One is explicit, there's more implicit. And all of them, they fall into this category of being quite explicit, right? So it's like I have points, and points are just directly points from on objects. And for the surfaces or for parametric curves as well, they directly map it, right, to the points on the objects. So their explicit representations, they have a lot of benefits. First, they have you map all the points directly, so you can get all these points. In general, you can And every point I have, let's say I have a Bayesian surface representations. I can basically sample 2 points and UV in this underlying lower dimensional space, and then going through that function, I map it to a point in the 3D space, right? So I directly get a point on the 3D surface in the 3D space. So all points are given, in some sense, you can say directly. I can directly get all the points. So it's very easy for us to sample points, right? So let's say I have this torus, and I have represented it using this f function. So now my question is, can you just sample some points on the surface of the object for me? This is so easy because I will just, randomly put in some u and v values. I just randomly sample those u and v values and then let them go through this function. And it will just, compute and give me some of the 3D points which are guaranteed to be on the surface of the object, right? So sampling is much easier. So what is hard about these explicit representations? The hard thing is, it's very hard in some sense, to test whether a point is inside or outside the objects. Similarly, if I represent a sphere as this function, and it's easy for me to sample points on the sphere, but it is hard for me to say, now I have a different, I have a query, right? I say this point 3/4, 1/2, 1/4. I have this point in the 3D space. Is it inside object or is it outside object? Right. I think we can maybe, actually, I'm not even sure about that. So it is actually kind of hard to test, whether a certain point is inside or outside object. So you can see that explicit representations is, it's all these representations, they have their own strengths and weaknesses. And for explicit representations, it's actually pretty easy to sample points, which are very useful because sometimes you want to convert them into, let's say, a collection of points, and then you want to apply whatever your point neural networks on it. But it's hard to test if a certain point is inside or outside object, which may have some issues. For example, let's say if you want to use a neural rendering methods, and nowadays a lot of these neural rendering methods requires a lot of these kind of queries about whether a point is inside object or outside object, what will be the geometry or density of object at a particular point, what will be the material, or what will be the radiance or color of the object at a particular point, right? So explicit representations are not very supportive of, it's not easy to run these operations on these explicit representations. So naturally people thought, okay, maybe we can come up with a different type of ways to represent geometry. And here I say implicit representation with geometry, but as you can see later, a lot of these neural rendering methods or deep learning methods, they just extend these implicit representations for not only geometry, but also for colors and appearance of objects in 3D. So the idea of these implicit representations is now that I want to classify these points. So I assume, if the points are on the objects, they're on the surface of objects, then they satisfy some certain relationship. So for example, for a sphere, what will be the points on the sphere, on the unit sphere? The constraint they satisfy is, square of x and square of y and square of z, when you sum them up, they equal to 1, right? So this is the constraint they satisfy for all the points on the sphere. All right, so more generally, you can write it down as, the constraint will be some function of x and y and z equals 0, right? So in this case, the fx and y, the function will be x squared plus y squared plus z squared minus 1, right? So that would be the function here. But more generally, you can think about it as, even for complex shapes, you can represent, and sometimes, these functions can be so complex that you don't even have a closed form. So how can I represent an f? I don't know. I just write it as a neural network. My hope is a neural network will be able to represent it. But in general, the idea is, you have some function or some constraints that the points on a certain object will satisfy. And this is the way you will represent an object, and this is called implicit representations, which started with geometry, but as I said, you now use it in all these different ways, representing textures, materials, appearance, and all these things. So the good thing about implicit representation, let's start with the bad thing. The bad thing about implicit representation is now it's actually much harder to sample points, right? I tell you, okay, this is the constraint. Let's say this torus satisfy, right? Okay, every x and y and z, if I put into this function and the output is 0, then yeah, they must be on the surface of this object. But then how can I get a couple of these x, y, z, tuples? That would be very hard because they're required to solve this function. And this function is maybe not too hard to solve. Maybe you can still solve that using some high school math. But when the function gets really complex, for arbitrary shapes, it becomes much harder to solve these functions. So it's not easy to actually now sample points on the surface of the objects if you are representing the objects implicitly. But benefit, the strength of that is now it's actually pretty easy to test whether a point is inside the object, outside the object. Because, if I want to do testing, I just have a query. Then this is so easy because it's inside or outside. I just send it into that function. I'll get a value, or the value is, okay, minus 1/8. Okay, this is smaller than 0. So, because I assume, the object is represented by this function, and all the surface point on the object, they satisfy that function equals 0. Anything that's, I would say lower than 0, it's negative. If the output value is negative, then the point must be inside the object. And if the output value is positive, then the point must be outside the object. Right. So now it becomes much easier to test whether a certain point is inside or outside object, although it becomes much harder to sample a number of points on the surface of object. So you can see now there's a clear trade-off between these implicit and explicit representations. Here we talk about geometry, but this distinction and the contrast between explicit and implicit representations I think is very important and fundamental. It is behind development of deep neural networks when they apply to 3D data in general, as we'll see later. Okay, so before it's been 25 minutes, so I promise I spend no more than 5 minutes, and then we're going to talk about deep learning. So before we talk about how deep learning can be applied to 3D representations in general, a little bit more on implicit representations is some other features of implicit representations. The good things about them is it's easy to compose them, right? So sometimes you feel like, oh, if I have to represent everything with a function, that seems great, if I have a closed form, but also seem very constrained because every closed form I can write it out. The geometries look very, very regular. So if I want to represent the shape of a cow, how would I represent that? What would be the function I can write for the shape of a cow? It's just not obvious. But the nice thing about implicit representation is you don't have to write everything in one shot because it's so easy to compose them, right? You can actually perform logical operations on these implicit functions. Let's say you have two objects and you find the unions or intersections or differences. You can, again, they're just values, right? So you put XYZ onto this function, you get a value. You put XYZ onto that function, you get a value. You can just do, arithmetic operations on top of these values, and that allows you to compute the unions or intersections or differences between these objects. And eventually you can compose them to develop pretty complex shapes. And this is actually, behind support a lot of these industrial designs when people are designing, complex parts for, I would say, when you're doing manufacturing you have to fabricate some complex shapes. A lot of these designs are done by these kind of CAD models, computer-aided designs, and they're composing these implicit functions using simple logical operations. And, you can also do things that beyond just logical. You can even add things up, especially if you have a distance function where every point is sort of like, the positive value and the negative value, the values actually have meanings because they indicate how far you are to the surface of the object. So you can even add them up, and this allows you to smoothly blend the shapes, right? So you can see like here, if I have a distance function, and here I just want to represent a vertical line. Okay, this is here, and then anything that's -0 is to the left of the line. Anything that is positive is to the right of the line. And then you have another line represented using a different function. So what happens if you add them up? If you add them up, then it naturally becomes an interpolation between these two shapes. Right? This is an example of doing things in 1D. But you can imagine, you can even similar doing things in 3D in the sense that, okay, now you can actually even blend these different shapes. And these distance functions can be arbitrarily composed and allow you to create actually pretty complex worlds like this. And this is not easy, but you can even think about, you can construct really complex with all the details worlds by just by difficulty, but compose these different functions. But they are actually very expressive if you're very good at it. Okay, so we said, okay, we have parametric representations that can be explicit, that directly give you points on the 3D surface, or we can have parametric representations like these functions, but they're implicit, right? So they're just like, okay, now you can only try to verify if the point is inside and outside an object, but then you can also compose them to build more complex shapes. And is that possible for us to also have implicit representations that are non-parametric, like point style, but then you also querying functions? Or sometimes they actually do have things like that. This eventually goes to methods like level set methods, right? So implicit surfaces are very nice because, as we said, it's easy to merge them, it's easy to split them, but sometimes, it's hard to describe, as we said, complex shapes in closed forms, right? You have a cow, how would you represent it? Okay, you can compose them, but if every time I have to query whether a certain point is inside a cow, you have to have hundreds of functions and you perform all these add and or, and, or, plus, minus operations, then it takes a long time. So what if I just pre-query, right? So I have a 3D space and I just sample, let's say, 100 by 100 by 100 grid, right? So, and then I have now 1 million points pre-sampled. And for these 1 million points, I just pre-compute whether they're inside the objects or outside the objects, what is the distance of these 1 million points to the surfaces for complex shapes. So you can pre-compute them, and then you can store all the values in the matrix. This is in 2D, but you can, this is for visualization. But in practice, this is in 3D, right? So you have a 3D matrix that store all these pre-computed values of the distance functions. So now you're sort of, in some sense, you still have implicit representations, but because you have pre-queried them, you turned it into a non-parametric representations. And even if you just look at this matrix, right, in 2D, you can now still find, okay, where the boundaries are. So where are the boundaries? They're just basically where, you have two adjacent values, one is positive and one is negative, right? So that means there must be somewhere in between that the point here, they satisfy the function fx equals 0, which means the point must be on the surface, right? So in that sense, you're sort of turning on parametric representations, which are implicit, into a non-parametric representations by pre-querying a lot of these points using the functions. And this allows you to have actually more explicit controls because, you can now visualize them. You can say, I have this matrix and I can visualize them based on their values. And this is used a lot in things like CTs and MRIs and all these like medical data. And a related thing is people may say, okay, what if I don't care about all these distance values? I can pre-query what's going on at all these points, but then I compute all the values, like say +5, -5, but all I care about is whether this is inside object or outside object, right? So if it's positive, I'll just treat them as 1. If it's negative, which means they're inside object, treat them as 0, let's say. So if you binarize them, then this gives you final representations, which is arguably the easiest to understand. This is called voxels. Right. So, you can pre-query where the implicit functions are, and then you have all these kind of, density sample grid. But now instead of storing, their distance functions, how far they are from the surface by going through the functions and give you +5, -5, you just binarize it. You only care about whether a certain point is inside objects or outside objects. Then you have a voxel representation, which is again like a 3D matrix. Can be 100 by 100 by 100, but for every point you have go through this function and query whether it's inside and outside objects. You have 1 or 0, and you can represent objects in a binarized way, right? So this gives you the final representation I'm going to talk about for objects in 3D. So I've introduced voxels in a kind of complex way, but from a different perspective, people may say this is actually very easy to understand because in some sense, voxels actually have a lot of analogy as pixels because pixels are like 2D matrices. And now you have a 3D matrices, and voxels is basically just a 3D matrix, right? So although you can see that they have connections with all the other ways that we can represent shapes. And the way I'm introducing it this way is, actually, when deep learning come in, right? So first, deep learning, when did it start, right? 2010. Deep learning has been there for a long time. But the modern deep learning thing is 2010, Geoff Hinton started doing that on speech recognition. And then 2012, they have AlexNet, which is run on ImageNet. So you've learned all these, and they're all in 2D. Okay, now people say, okay, what if I want to do it in 3D, right? This is a very natural thought. So I want to go from 2D convolutional neural networks. 2012, there's no transformer, right? So how can I apply a 2D convolutional neural network on 3D data? And everyone knows we have all these different 3D representations. But which one to begin with, right? It turns out that people will say, okay, yeah, the people who started doing deep learning on 3D data, they're the computer vision people. They're not like the graphics people. They're like, okay, I've been working with pixels, and maybe the easiest thing I can do is just to, scale up. And instead of working on 2D matrices, I just make it work on 3D matrices. So that would be the simplest thing I can do. Instead of having a 2D convolutional neural network, I have a volumetric convolutional neural network. Then, which of these representations allow you or support a volumetric convolution? Right? It turned out to be this voxel representation. This is basically the easiest you can imagine. Right? So But the graphics people do not agree with that because the graphics people are like, oh, this voxel representation is really bad because it's very slow to compute as we talked about. We have to pre-sample all these values, and there, you can look at the quality, right? It is so bad compared with meshes or point clouds. So people are like, why do you want to start with that? But the reason that people started doing deep learning on 3D data with voxels, because I think it's like, it's so easy to draw an analogy between pixels and voxels, and you just have to change one of the code. That is, instead of doing 2D convolution, now do 3D convolution. Right, so that's sort of in some sense how things get started. Okay, but before I talk about the deep learning methods for 3D data, another aspect that's very important is the data, for 3D data, yeah. So beyond methods, data sets are also very important. ImageNet really prompted AlexNet and stuff like that. So for 3D, similarly, we have to collect a lot of data as well. So pre-3D, pre-deep learning, the common data sets, the popular data set people often use is this thing called Princeton Data Shape Benchmark, which has 1,800 models, 180 categories. So you can see they actually have quite a lot of categories, 180 categories. But there are only 1,800 models, which means there are like basically 10 models per category, which is so small. But back then it was considered pretty large, and people feel like, oh, this is already enough to do because we can't really make any of things really work well on them. And there was very little machine learning there. So prior to 2014, all these data sets are kind of more or less small. They may have a certain number of models, even up to 10,000, 9,000, 10,000. But, they're also divided into so many different classes. And so each class, you only have like 10 models-ish, or less than 100, I would say. So after that, people started by saying, okay, if we have ImageNet, can we also have the 3D data sets for shapes? So this is behind efforts of a few concurrent work, but really I think eventually they sort of consolidated into this thing called ShapeNet, which is, a lot of them are actually led by Stanford. There's Leo Gibas and Silvio Savarasi. So they led this kind of large data sets called ShapeNet, which has 3 million models. And so, but in practice, just like ImageNet, you have this large ImageNet and there's a smaller data set that people often use. So ShapeNet, similarly, you have a ShapeNet core data set, which is what people typically use as basically 50,000 models in 55 categories. Now you can see for every category you have 1,000 models on average. But in practice, it's not that balanced. So for chairs, you have actually a lot more. So that's why, people say, oh, now finally I have thousands of models on chairs. I can train some deep networks on it, right? Before you have 10 models, you can't do anything. So that's how things started. And so there has been a few years where a lot of these advances and all the results are just presented on chairs and cards because these are like the largest categories in ShapeNet. And people feel like, okay, that's great, but then that's not enough. So we should move, even bigger. So in the past few years, this is work at AI2, the Allen Institute from Seattle, where what they did is they collected much larger data sets called Objectverse and Objectverse Extra Large, that you have roughly 1 million or 10 million models for different 3D assets. You can see they have much more categories. And they also have, these models on average also have higher quality, also with textures. So these are synthetic data sets, but also there are real data sets that are being produced, including, some of them are from like 3D scans. You just take 3D scanners. Back in 2016, people have been working on it. This is a data set called, I think, the Redwood data set or something. So you have like 10,000 scans of real world objects. And more recently, people have been building larger data sets where they also encourage people. I think this is an effort co-led by Meta and Oxford. So they encourage people to take data for them. They also pay people to take data for them. So people just using an iPhone, you have an object, put it on the table, you use an iPhone, you take a 360 video around the objects, and then you get $1 or something like that. So they encourage people to take data for them. This is the first version. They have 19,000 videos of objects. These are like real objects, right? Because capturing real objects is much harder. And the Objectverse and all the things I talked about before, it was like synthetic objects. But these are like real objects. And then also because a lot of the development in 3D vision algorithms, you can actually take these 360 videos and trying to reconstruct the 3D objects. So now you have paired data of the videos or images of objects as well as their 3D geometries and textures. This is their first version. I think they have a more recent version, V2 or maybe even V3 right now, which is supposed to be a little larger. But still, it is kind of hard to scale up. Think about it, right? Now you have like 90,000 videos or basically 90,000 objects. And I think they're scaling it up, but I don't think it's over 100,000. So basically, you can think about it as for real objects, you have like 100,000 models. But if you look at what's the data set size of the images, right? So it's like, I don't know, Lion 5B or whatever, that's like 5 billion images, and Google and OpenAI must have much larger data sets. So there's still kind of a huge gap between the number of data points that you can have for 2D images or videos versus you can have for 3D objects. So I think that's a kind of a big challenge, how we can move forward with 3D vision. And people have different ideas. But still, this is much larger than what we had before. At least you can, it's possible that you can still more or less train some deep learning models on these data sets now. And quickly, there are also other data sets that people being built on parts. This is also from Stanford, where they try to annotate a little bit of object parts and their correspondence and hierarchies. And also there's this data set called PartNet, where they want to annotate not only the parts and their semantics, but also how they may move. Also a little bit of mobility information of different parts, like laptop, you can open and close it. And there are also data sets for 3D scenes. So not only just objects and parts, but there are also the rooms. So they're having things like the scan data sets, like, these are people actually just go inside your home or go inside to our office as well. They just come in and then they just have a 3D scanner, they scan the home, and then they have some annotations. So, here, and more recently, again, you can do that even with your iPhone right now. But still, these kind of data sets are much smaller, right? So here, this one, the first version of scanner, you have 1,500. I think they have a plus with the second version, which is roughly the same size, maybe 2,000 or 3,000 rooms. So the amount of data you have for 3D data, for 3D scenes in particular, is also, even much smaller than the amount of data you have for 3D objects. So I think it's not obvious that how can we go beyond that constraints, because if you have to scan it yourself, you're always bounded by how much time you have and how much people you have. Anyway, but there are attempts being made in trying to collect data. Okay, and finally, if we want to apply deep learning onto 3D vision, so what are the tasks we care about, right? So there are generative modeling, just like what Justin said, you can generate 2D images or videos. You can also generate 3D shapes. You can generate 3D scenes. You can make them conditioned, right? The condition can be conditioned on language, conditioned on image. You have an input image, and how can you reconstruct the 3D objects? And you have to learn the shape priors. You have to do shape generation, completion. Sometimes you have partial objects, and you want to, repair it. You want to fix it. So there's geometric data processing as well. Other tasks, including discriminative models. For example, you have a 3D shape. How can you classify what's the category of objects it belongs to? Is it a chair or a table? And a lot of them now actually done by rendering them into pixels, right? Because you have very good, image recognition models like GPT or something, right? So you just take a 3D object, you can render them into a picture. You can upload a picture to GPT, and they can do it for you, right? So that's in some sense one way of solving these discriminative problems. But there are also more specific things that it's not very easy to solve. For example, you have a different type of cell, and you have the 3D scans, and how can you classify the cell, and all these kind of more specialized domains where you don't have that much data. So how can you solve these discriminative problems? In joint modeling of 2D and 3D data, which is becoming more and more important because the 2D data, we have so much more. We have so many images and videos. We have very good foundation models that got trained on them. So how can we leverage the priors in our 2D foundation models, like what an image look like, how to make an image look realistic, how to make a video look realistic, how can we use that information to help our 3D reconstruction to be more realistic? Right. So joint modeling of 2D and 3D data, because there are so many large-scale 2D data sets and very good pre-trained models. And also there has been a lot of advances in neural rendering or differential rendering methods that basically connect 3D world and 2D world. Because you have 3D world, you have 3D model, you can render them into 2D. The rendering process, can be made differentiable or can be even approximated with neural networks. Then now you can connect all these data in different modalities through differentiable neural networks. It allows you to bridge the priors you have in 2D data or 2D foundation models into the 3D world. Yeah, and then, sometimes you want to even do some joint multimodal beyond visual data, including textual data, but sometimes you have other data. Let's say in robotics, you often have tactile data, so how to fuse them as well. And sometimes for autonomous driving, maybe you have LiDAR data or depth data. How can you fuse them as well? So we want to use deep learning on 3D data to solve all these different problems. So we spend all the time talking about representation, so how do we begin with? So as I suggested, people who are initially doing that is the computer vision people. They work on pixels, they work on images. So naturally they say, why don't we start with voxels? But even before that, they say, okay, And this is the old idea, and this is the very first idea that people tried in applying deep learning to 3D vision. And now in some sense it's coming back. But the very first idea they tried is, let's don't even worry about voxels. Let's just say you have a 3D shape, it's a mesh, it's a voxel, whatever. I want you to learn to recognize what the object is, right? What is the object here? It's a chair, but what if the input is 3D data? How can we process that? Before we have a 3D deep learning methods, what if I just render into images? Because I have very good image models. I'll just, render, just take the 3D objects, I would just put camera at different places, I can render all these images, the objects from different views. And then, now this becomes a 2D problem. I would just apply a convolutional neural network, on each of these views. And I have some ways to fuse them, right? So I have some pooling, whatever. And then I just do an image classification, So this becomes an image classification problem, while the only difference being now you have multiple views. Right. So this is in some sense one of the very first idea people applied to 3D vision. They just use 2D networks. And why do you want to use 2D networks? Because back then they're pushing on ImageNet and they're very good. So they have ImageNet is much larger than 3D data sets. So any model that are pushing on ImageNet, they have very good performance. So the easiest way to solve the 3D recognition problem is to first render into 2D. Later, people sort of move away from it because people are like, we have more 3D data. We should try to do 3D native, come up with 3D native methods. And people also, come up with ideas about connecting 3D and 2D through neural rendering. But now I feel like this trend is coming back because, all these image and video models are getting so great. I don't know, many of you may have seen the VO3, whatever was released yesterday, right? So if they're so great, maybe we should just rely a bit more on the image and video foundation models, again, because they're just training on, 1,000 times or tens of thousands times or even more than that, and maybe a million times more data than 3D data. So how can we incorporate that? But anyway, coming back, this is the very first method. In some sense, people tried to apply deep learning on 3D data just by converting them into 2D. And they do very well in image shape classification. They have shapes and you want to classify them into different categories and they have very good performance. So you can leverage a lot of literatures on 2D image filtering models. But the issue is you need some projections. But sometimes, the input can be very noisy. People are like, what if my input is too noisy? The point clouds or whatever, they're just not very good. If I render them, they look kind of bad. So is that possible for us to come up with more 3D native methods? So later, people tried a number of 3D native methods that just apply deep learning directly on 3D data. As I said, the easiest way to do this is just to apply your pixel convolutional neural network into a voxel, volumetric convolutional neural network. So this is actually a deep leaf network, which is a generative network. But still, you have some 3D convolutional features. And this is in 2015 by Princeton. And you can see that they learn a generative model that can actually synthesize 3D shapes in the form of 3D voxels at relatively lower resolution. But this is 10 years ago now. So back then, this is considered kind of pretty impressive. And you can do all these condition generations, conditional semantic labels at beds and a desk and tables. So you can synthesize these different shapes. And because this is a generative network, you can also use it for classification. So you can do image shape classification as well. And later, something that actually we did is, what if we just applied on GANs, this generative adversarial network? You can use GANs to generate 2D pixels. There's no reason you cannot use GANs to generate 3D voxels. So just this very simple thing that is applied again to 3D voxels and actually give you a pretty good generation of 3D objects. This is 9 years ago. Yeah, okay. And later, with Jun Yan from CMU, we also did an extension. That is, you can use GANs to not only generate 3D shapes, but also you can render them into 2D. You can project them into 2D surfaces so that you can get the depth map of the 3D objects you generated. And then you can use a cycloGAN to convert this depth map into a color image. Now you can have adversarial losses not only on 3D shapes, but also on 2D pictures, right? You want the 3D shapes to look realistic so that they can be indistinguishable from the 3D object data you have. You also want the 2D images to look realistic so that they're indistinguishable from images of real cars. So then you can do 3D generation as well as 2D generation at the same time. And because you have different latent vectors for the shapes, for the viewpoints, and for the textures, you also have some level of controllability. Like you can change the viewpoint, you can change the textures, you can do interpolation, and you can transfer the texture of one car onto the shape of another car. And this is 2018. So people tried applying deep networks, like convolutional neural networks, generative adversarial networks on 3D voxels instead of 2D pixels. And can we do a little bit better with voxels? Because one thing that people have complained about voxels is they're just like really slow, right? You have to pre-sample them, and there are a lot of wasted effort because a lot of the sample points are just like empty space, or they're inside the object and it gives you no information. So naturally people thought, okay, can we actually make it better? So there are improvements to voxels like octave trees. The idea of octave trees is you still have explicit representations. In some sense you can argue it's an implicit representation, but it's like non-parametric implicit representations. But then instead of representing every point in the space at a uniform scale, right? You actually, assuming the voxels basically the voxels can be of different sizes. I just divide the space into like different regions, and I spend a lot more. And when I feel like I'm really close to the surface of the objects, I just represent objects at a much finer scale. And when I'm like in this empty space or inside objects where I really don't care too much about what's going on, I can have like huge voxels in some sense, right? So you can recursively partition the space, and you can have, different sizes of voxels at different space. And this allows you to really scale up. So you can see that compared with just directly using voxels, this is 2019-ish. People say, okay, octave trees are great because it allows me to go from lower resolution. That's how much you can fit into GPU memory, right? You can do 64 by 64 with voxels, but with octave trees, you can do 256, right? So, and then you can even use that for generation as well. You can generate objects, also, they look like voxels, but they're kind of higher resolution because you're more efficient in representing the space. So these are like the very early attempts in applying deep learning to 3D space, and they're like, okay, why don't we just try voxels? Then, this is the moment where people get a bit more interest into like, oh no, now what if, the graphics people feel like, you're just doing all this wrong, right? Because why do you want to use this kind of pretty inefficient, ugly looking representations like voxels or octave trees? No, we have all these good representations, point clouds, meshes, splines. Why are we not using these representations? But as we said, the challenge is, points are just here and there, right? How can you even apply convolution on points and stuff like that? It's just not very obvious. But people start to look into it. So naturally, people move into applying or developing new deep learning methods that directly work on not only just 3D data, but also different types of 3D representations like point clouds. So in point nets, I think this is an important work also from Stanford, from Leo's team. What's going on here is they develop a new type of deep network that directly work with 3D point clouds. So it's called point net. So the idea is, for points, you have to be permutation invariant. Right? Because, if I have 0.1 and 0.2, okay, like 0.1 is here and 0.2 is here. Okay. Now I have a, different input. I would say 0.1 here and 0.2 there. Right? So then, whatever, your network should be invariant to these different two types of input, which means, no matter I name this one is 0.1, that one's 0.2, or I name this one's 0.1, that one's 0.2, your output should be the same. Right? Because the points, they're like kind of unordered. There's no guaranteed ordering in the sense that our top left is 1, 1, bottom right is 100, 100. Right? So if if the points are unordered, you have to be permutationally invariant. So how can we do that? And second is you have to be also sampling invariant. So sometimes you sample like say 10 points on the head of the bunny or a rabbit, and 5 points on the tail of the rabbit. And sometimes you sample 10 points on the tail of the rabbit, only 5 points on the head of the rabbit, right? So how can you also be invariant to that, right? Because there's no guarantee on how you sample points. So there's kind of a bit of a issue here and there. But the one idea they used, and I think it's basically probably the most important in point net, is they just, I just apply, it's also so simple. I just apply a symmetric function on the embeddings of the points. So basically, for all the points, I first compute some embeddings for them, just like you will compute embeddings for different regions or different windows of the image. And I compute the features for each point, and then I just have to fuse them, but because I want them to be permutationally invariant, right? So I just use a symmetric function, in the sense that, for example, it can be just a max function, and then I take the maximum, softmax. It can also be a sum function. I just add them up, So that's what's going on. This is so simple. You have a number of points, 1, 2, 3, 1, 1, 1, whatever, and then you have to compute embeddings for them, and then you just aggregate them. You can say you compute the max for each dimension, you can sum them up or stuff like that. And yeah, and then you have this aggregated embeddings for all the points, and then you go through maybe a few layers of fully connected networks and stuff like that, and then you use it to classify, are these points really representing a chair or a table? So that's basically what's going on. And it turned out to be quite powerful. And of course, there have been a lot of the improvements on top of that. People have been coming up with new methods that improve point.NET. They have point.NET++, and there are things like people have been trying to do is like graph neural networks, because you can easily translate points into nodes of a graph, and then the neighborhood, the proximity, whether two points are close to each other, as the edges connecting these points. So there have been like graph neural networks and all these other methods that have been developed for these point cloud processing. But the original idea in the point.NET paper is kind of so simple and turned out to be also very powerful. Something else you want to consider is you also want to measure, for pixels it's easy. I have an output image, I have the ground truth image, I just compute differences between the two. I have an L2 loss or whatever. For points, how would you compare the output point cloud and the input point cloud? Right? Especially if you care about generation tasks. If you do a classification, that's fine. You have input point cloud and output is, chair, table, whatever, you have a cross entropy loss. That's all you need. But if the output, if you're doing a generation task, you have a voxels, it's also easy, right? Just do a cross entropy loss of the 100 by 100 by 100 voxel grid. But if your output is a point, 100 points, then how would you compare the output point cloud versus the ground truth point cloud? You have to also design distance metrics. So the two common distance metrics that people did use, one is called the chamfer distance. Chamfer distance is easy to understand. That is, you have two set of points, and for each point on each side or each set, you've just basically find the nearest neighbor, right? So you have a collection of red points, you have a collection of blue points. And for the red point, for each of the red points, you just find its nearest neighbor in the blue set. And for each of the blue points, you just find the nearest neighbor in the red set. And you want to minimize the distance, minimize the distance of each point to its nearest neighbor in the other set. And the second idea, loss function that people may use, is called earth mover distance. And here you do a bipartite matching between the two set of points. And you have a one-to-one paired matching between these points, and then you want to minimize distance among all these pairs. So these are the two common metrics that people use when they're comparing the distance between the point clouds, and they can be made differentiable, which means you can now compute the gradients and use it to optimize your neural network, so that hopefully they output better point clouds if you're caring about a point cloud generation problem. So we have moved from voxels to point clouds. And then people are like, okay, this is great. And now I can process the points, I can output points. But we also have other, beautiful representations like splines. They're very good at capturing the surfaces of objects. If you use any kind of neural network to generate voxels or generate point clouds, they always look very ugly, right? So they don't have smooth surfaces and stuff like that. So how can we have a neural network that can output or understand objects, but also represent the beautiful surfaces? So people go a bit forward in thinking about how I can integrate neural networks with things like splines or functions like that. And a notable example here is the thing called AtlasNet. So what's going on here is they try to use deep learning, but then instead of directly outputting a set of 3D point clouds, right? So I learn a transformation function. I have a latent shape representations, and then if you remember, right, when we say you have these parametric representation for object shapes, you're basically transforming, let's say, a 2D space of U and V into a 3D space, like a sphere. So, and for simple things like sphere, it's easy. You can write it down, right? What is that function? In sine, cosine, whatever. But for complex objects, it is very hard to write a function, and often there's no closed form. So the idea here is, okay, if there's no closed form, then why don't we just use a neural network to represent it, right? So here you can see this neural network, which is implemented as an MLP, just learns that function f, right? You can take the two values u and v as the input to the function f, and the neural network is performing the computation of that function f and u and v and output a point in the 3D space. So it's basically learning how we are able to transform this kind of 2D space into the 3D space. And it might be too hard to represent the entire object using a single transformation. So people thought, okay, we can use a couple of small neural networks. So think about it as now you have a piece of paper, you can fold it in different ways, and you can fold it multiple times, and all these things get put together to form the final shapes you care about, right? So this is, you can see the differences between these three different representations. You have an input image, and if you want to represent it and reconstruct it using voxels, you can see it's doing something, but you're really bounded by limited resolution voxels. And for point clouds, yeah, you're no longer bounded by the resolutions, and it gives you maybe a bit more details, but points are really unordered. You cannot really get any smooth surfaces out of the point clouds. And for this thing called AtlasNet, which is basically learning to transform pieces, you can see that they have actually smoother surfaces, right? So using neural network to represent how you can map a parametric representation from lower dimensional space to a higher dimensional space, and you learn multiple of these mappings, and when they're combined, that gives you the final output geometries conditioned on 2D images. Okay, so finally, in some sense, we can put it this way, right? So what is deep network doing when they're doing image net classification, right? They're basically learning very complex functions that map input images in the form of pixels into a final category label. Is it a cat or a dog or a person or whatever? That function is really complex. And output space is really small. Output space is like, 1,000 dimensions, right? So it's like, okay, is it a cat or a dog? You have 1,000 with classification. Output space is so small. Input space is much larger because you have, 500 by 500 pixels. So that's 250,000 or something, right? The input space is much larger. Output space is really small. The function is really hard to write. How can you, is it possible for me to write down some formulas so that I can classify the input image by computing whatever some specific values and output if this is a cat or a dog? I cannot do that, right? The function is so hard to write. There's no closed form. That's why I need a deep network. Input space is large. Output space is small. So if you really think about deep networks that way and think about what they are doing, then you realize, a lot of the things that we have been doing with deep networks on 3D shapes, it doesn't seem to map that, map into that, I would say equation, right? So it doesn't map that well. And what are the representations that really map it the best, right? What's the optimal representations that seems to really fit into the paradigm? And if we think more carefully, I think around 2019, when people realize, oh yeah, in some sense, deep network is an implicit function, and why don't we just use it to represent an implicit function for object 3D geometry? Right. So instead of representing the kind of voxels, because now you're just doing, you turn it into pixels but then you just scale up into 3D and you apply 3D convolution. Okay. But, fundamentally voxel is really about, whether the thing is inside and outside the object. So instead of just directly pre-querying the space and get the voxels and apply convolution on top of it, what if I just directly using deep network to perform that query for me? So that I don't have to run 3D convolution or anything. I just query a space in 3D, and deep network should tell me, if the output can just be one-dimensional, inside and outside, right? Whether that point is inside the 3D shape or outside the 3D shape. So finally, I think people move that leap, take the leap to go from explicit representations on point clouds or splines into implicit representations, but not directly working on voxels, but instead, think about it as a level set or some implicit functions that use deep network to represent, that's the final step, right? Going from these atlas now, whatever, you're learning the transformation from a 2D space to the 3D space, but now I can directly do an implicit query using the deep networks. So that goes to deep implicit functions, which is kind of interesting because around that time in 2019, there are like 4 papers that are doing almost exactly the same thing. They all argue that before we have been using voxels and point clouds and meshes or whatever, they have their own strengths or weakness. But really the right thing to do is I should just send, the query into the deep network. So deep network, what it should do is it should take the input, let's say XYZ coordinate, and output whether that point is inside and outside the object, And that would be, in some sense, the final, I would say, one of the final, and that's the kind of idea that was proposed in 2019, and even right now in 2025, right? A lot of people have been still using this kind of same idea. That is, I would just use deep network to tell me whether a point is inside and outside an object. And not only, you can go a little bit beyond than just like a binary classification of inside and outside, because you can also say, oh, maybe I care a bit more. I say, what would be the sign distance function? How far the point is from the surface of the object? Or what will be the density values of the point? Or later, what will be the color? What will be the radiance values of the point? Right. But here, starting from 2019, people really start to, apply deep network in a way that is in some sense similar to classification. That is, I take points in 3D space and use it as an implicit function to query, some properties of the points in the 3D space. And, people have tried to use it as, represent a collection of implicit functions, not just like how pieces are deforming into the 3D space to get different pieces of papers in 3D, but really representing implicit parts of the objects using small neural networks, and they can form complex shapes. If you can represent objects in 3D using implicit functions, you can do that not only for geometry. You can query not only the inside, whether a point is inside and outside objects, whether how far the point is from the surface of the object. You can also query what will be the radiance, what will be the color of the object. And then I go directly 1 year later, this is maybe 1 or 2 years later, people come up with this thing called NeRF, right? So where they used, the differences here is now say, I should use deep network not only to query what will be the sign distance function or density of the objects, but also querying the radiance. So here you can see what's going on is you query NeRF about XYZ coordinate in the 3D space. In addition to that, because you're trying to model the appearance as well, you also query the viewing directions, right? The camera viewing directions. And the output of the neural network is not just like 1 or 0, inside, outside. It is the density values in addition to the color values, right? The radiance. And if you directly train implicit functions on 3D shapes, and then you require 3D supervision, right? So, if you have a collection of 3D objects, you can use them as a supervision that give you, okay, you have the ground truth about whether a point is inside or outside a 3D object. But here, you want to train on 2D images. That's what's going on with NeRF. So they also put that together with the neural rendering, volume rendering function. And they made this volume rendering function differentiable in the sense that you can have a rendering model. You can query all these different points in the 3D space. You can get their colors and also their densities and appearances. And then you can compute how much light is blocked along the way, right? So this is basically volume rendering as in computer graphics. There's very minimally change made because you can see even directly from the volume rendering equations that everything here is, this is an approximation, but with that approximation, everything here is sort of differentiable. So you can compute, how much light, if the neural network gives you the density, which is basically like you can think about it as opacity of the point in the 3D space, and also give you the color, then you can compute how much light has been blocked by the points that sampled ahead of that point and along the ray. And you can compute also, how much light is there contributing to what I'm going to see in this ray from any particular point, right? So now you have a few things. You have neural network to represent the implicit functions for the colors or radiance and the densities. And then you have this volume rendering equations, which is made differentiable so that you can learn directly from 2D images. So these are the two things that have changed. And one is I no longer have to train on 3D shapes. I can train on 2D images with this volume rendering equations. And the second is instead of just looking into geometry or density of objects in the 3D, I also look into their radiance or appearance in 3D. Right, so these two changes lead to the kind of big jump behind, from NeRF or from implicit functions, deep SDF and all these earlier methods to NeRF. So a lot of people feel like, okay, yeah, NeRF has been great and seems like out of nowhere. That's really not the case because, they're very much inspired. If you look at the articles they later wrote themselves, they are very much inspired by all these advances in deep implicit functions, although they focus only on geometry. But now I do both geometry and appearance, and I do learning from 2D images instead of 3D shapes. So yeah, here are some results of NeRF. This you may have seen many times. Okay, so if you remember, we said, in the past we have been working on something like generating 3D shapes, and then also generating their 2D appearances. Here at the very beginning, we used the representation that is voxels. But now, as we said, NeRF is great, and if we have implicit representations, there's no need to really represent it as a voxels. What if we just replace that with the radiance fields, right? So we also did that as well. So we have a neural network that captures the implicit radiance fields and densities, but it is generative neural network. And then you can even still apply the same GAN rendering framework so that you can render objects in 3D as well as their 2D pictures. And then you can also do the same thing as controllability. And you can change the camera viewpoint, you can change object identity, but then you can keep the viewpoint. You can do all these things that we can do before. But now with NeRF, you can learn directly from images, so you don't have to restrict yourself to the categories of cars or chairs where you have a lot of 3D data because you can learn directly from images. And yeah, so you can see that now the output becomes much more realistic. So this is the thing we did called PyGAN with Eric Chen as a first author, and also with mostly people from Gordon's group. Okay, and finally, NeRF is great, but then NeRF has this issue that is, you have to sample a lot of points in 3D. You're no longer pre-sampling them and then applying a volumetric convolution, but still just like a level set, right? You have to sample all the points and carry neural network all the time. And now you can do it learning from 2D, you can do all these great things, but because you still have to do all this sampling, it is very slow. So people thought a little bit more, again, from the graphics people, they're like, okay, I have this good idea about points and matches. And the nice thing about them is they're free in space, they're very efficient. So is that possible for us to integrate the two? Can I have implicit representations, but maybe I don't have to have a fixed sampling grid. I don't have to sample all the times because it takes so much time. So maybe I really should put them together. Right, so you can argue that NeRF try to parameterize densities, parameterize the scenes very, very densely. You have to sample all the points densely in 3D. A lot of points are wasted, just like in voxels. You have all the points that are representing empty space. You don't want that. In NeRF, a lot of samplings, a lot of queries are also querying empty space. And network may give you like density 0 or something like that, but it's taking a lot of time. So how can we address that? What if I just try to sample things more sparsely, right? I still have this implicit representations, but instead of, sampling empty spaces all the time, I only sample at places where I know there are stuff. But how can I know that? What if I have a point representations? So this is the idea behind this thing called Gaussian splats, which you may have heard of. So it still has the same implicit functions. You're querying neural network for densities and for appearance and stuff like that. But instead of querying neural network all the time, I have a point representation. I have these kind of 3D Gaussian blobs in the 3D space, which I think sometimes you can think about them as point clouds. But the points are not like a single point. They're like a blob. They're like some regions. Because you know where these blobs are, when you're sending out a ray from your camera to the 3D space and sample points, you don't have to sample all the time. You just look at where these blobs are, and then you can, based on their the radius of these different Gaussians, you will only sample at regions where you know there's some stuff. So this makes rendering much more efficient. And so here are some of the reconstruction results using 3D Gaussian splats. And you can see that, in terms of quality, right, they're actually, not that, they're comparable. I would say they're comparable to NeRFs. This is like different metrics, PS and RSSM, they're like rendering qualities. And I think the x-axis, the y-axis it doesn't start from 0. So this is a little misleading, but basically you can see these numbers are really close. So in terms of quality, rendering quality, Gaussian splats and NeRFs are similar, at least when they're first proposed. But Gaussian splats are just much more efficient, right? So this is FPS, frame per second, right? You can render 150 pictures per second. While for NeRF, it takes you like maybe 20 seconds to render just a single picture, right? So now this thing is now made 1,000 times faster. At least that's what they argued. So because you no longer waste all your computing power on simply empty space and querying neural networks all the time on these about these points that are in the empty space. Okay, yeah, so that is basically how deep learning has been integrated on 3D data in all these different representations, how they got started, how they have evolved, and its connection with all these different shape representations. And one thing we didn't talk about, just use 2 minutes to quickly cover it, is there has been also interesting things about object geometry that is not only about the element geometry, the specific details about the parts, but also the structures, because often there could be, the shapes are symmetric, right? So we talk a little bit about it, where like there's a parametric surface, and you can parameterize part of a surface using like a sphere or stuff like that, using these kind of closed form equations, and that gives you a little bit of symmetry. But there has been also more systematic studies about the regularities or structures within object geometry, including their repetitions, including their symmetries, and people can also come up with different representations for it as well. So how can we really represent, in some sense you can argue that point clouds, meshes, implicit functions, they're really representing the geometric details maybe for the individual parts. None of them is directly capturing things like regularities like symmetry or repetition. So how can we capture that? A few other attempts that people have been exploring, mostly from the graphics community, is, I can represent objects just basically as a collection of these simple geometric parts, like a part set. But I can, and there has been methods that apply deep learning on it, representing, using deep networks to represent different parts of the object using simple geometric primitives and then compose them, or, using implicit functions and compose them, as we talked about before. But, there has also been attempts to do a bit more, right? So not just like representing objects as a collection of parts without considering their relationships, but also modeling the relationships between these parts. This is, even more so the case for scenes. Let's say a bed is usually next to the wall, chairs is usually next to the tables and stuff like that. So you not only want to represent them as a, unrelated collection of parts or objects, you want to capture their relationships as well in the hierarchies. When you are constructing, when you're building, you're doing some constructions, your architecture, you're architecting or designing a building, then you, of course, you're not like just like representing objects or their relationships. You have to consider the hierarchies, what you build first. There's a classroom, and the classroom has, there's some tables and chairs in it, and chairs has parts. There's basically a kind of level hierarchy, and how this can be used and integrated with neural networks, as well as, you have not only the hierarchy, but also you can compose hierarchies and relationships, right? So you have a hierarchical graph, where let's say for chairs, you have different level hierarchy for bases, for seats, for backs, and the bases may have, different legs. But then also the legs themselves are related, right? The left leg of the chair and the right leg of the chair, they're supposed to be symmetric, and they should have the identical shape. There are constraints on where these legs are. They have to be, really aligned. Otherwise, the chair is going to fall. So there are all these constraints that are sort of, pretty useful. And how can we represent them? And people come up with all these different representations. And for each of them, there are also, a lot of neural networks, deep learning methods designed to learn and to capture and to generate objects that satisfy all these constraints. For example, like you can see, this is a kind of hierarchical graph encoders and decoders that try to represent and generate 3D chairs that satisfy all these constraints while maintaining their hierarchies. Right. So I think this is also from Leo Gilbert's group from 2019. And, sometimes we can even represent shapes using some form of programs, right? Because there's repetitions and for loops, and how this can be incorporated into using neural networks to generate programs that synthesize object shapes and synthesize their relations between these object parts, and that's also an important topic. And most recently, I would say, let me end it by saying, I think there has been a new trend just in the past 1 year or two, that the deep networks or large language models are doing so well, and they understand things so well that people are exploring, is it possible for us to just use large language models like GPT to output these programs, right? Because they understand the semantics and what the chair should be like, what are the constraints the chair should satisfy. So is it possible for me to use a large language model to output programs, but then maybe I can use some implicit functions or whatever, right, to capture the specific geometric details of the parts of the objects like the chairs. So there's some kind of new emerging trend of research that is happening right now in these days. Okay, I think that's all I have. Thank you.